As Richard finds things, I'm John Offenberg, US EPA's Office of Research and Development, and this is Summer Streets, the Minnesota Pollution Control Agency. And we're going to shift gears closer to the very beginning of the whole conference and talking a bit more about air toxics and contaminants of emerging concern.
Okay, well, let's welcome our first speaker. I hope I pronounced her name correctly. It's Irina Nestorescu from York University.
Hi, my name is Irina. I'm a graduate student working with the Vandenborre Research Group at York University. I'll be presenting some of my research into the measurement of gas phase perfluoroalkyl carboxylic acids using passive air samplers. First, I'll provide you with some background information. Perfluoroalkyl carboxylic acids, or PFCAs, are a class of poly or perfluoroalkyl substances, PFAS, widely known as forever chemicals. PFCAs are man-made compounds which contain a hydrophilic carboxylic acid group and a hydrophobic, fully fluorinated alkyl chain. PFCAs have become chemicals of environmental concern due to their toxicity, persistence and stability in the environment, high mobility, bioaccumulation, and long half-lives in humans. And due to their unique and useful properties, they are widely used in industry worldwide. PFCAs fall into two categories based on chain length. Long-chain PFCAs have 8 or more carbons, and short-chain PFCAs have between 2 and 7 carbons. And then the short-chain group also contains a subcategory called ultra-short-chain PFCAs, which have 2 or 3 carbons. PFCAs are everywhere. They are ubiquitous and extremely persistent in the environment. A wide range of PFCAs are expected to endanger both animals and humans as they have the potential to bioaccumulate and cause serious medical issues such as cancer, liver damage, and infertility. Restrictions on the production and use of long-chain PFCAs such as PFOA have resulted in the use of shorter-chain PFCAs as substitute, and consequently, increasing concentrations of the ultra-short-chain PFCAs, TFA, and PFPRA have recently been detected in the environment. Pollutants like PFCAs and their precursors are released into the atmosphere in the gas or aerosol phases, and they can undergo long-range atmospheric transport, leading to their worldwide distribution via dry and wet deposition. The measurement of PFCAs in the atmosphere is important for species that do not readily deposit. And this measurement is usually done using active sampling techniques, which can be challenging, particularly in remote areas, due to their high cost, high maintenance, and power requirements. Passive sampling is a cheap, power-free, low-maintenance alternative to active sampling. My research objective is to develop a fully validated atmospheric passive sampling method for ambient monitoring of ultra-short and short-chain PFCAs using ion chromatography mass spectrometry, or ICMS, for analysis. This will enable more widespread research on contamination levels and long-range transport processes of PFCAs, and such research is essential for a comprehensive understanding of the risks that PFCAs pose to the environment and to human health. Our research group developed these passive air samplers, or PAS, for the measurement of gas phase PFCAs. Figure 1 is a schematic of our custom-built passive air samplers, which are composed of a petri dish, a nylon filter sandwiched between 2 PTFE rings, followed by an overlying polypropylene, or PP, filter, and then a polycarbonate ring, which seals everything together inside the petri dish. This PAS filter pack is then enclosed inside a weatherproof cap, which protects it from wind, precipitation, and sunlight. Figure 2 shows the proposed acid-base reaction for the adsorption of PFCAs to the nylon filter. And in Figure 3, you can see that the overlying polypropylene filter blocks particles and allows gases to permeate through to the nylon filter, onto which gas phase acids, including PFCAs, selectively sorbed. The uptake rate of PFCAs to the nylon filter is determined by the rate of diffusion through the PP filter and the rate of adsorption to the nylon filter. and this rate can be negatively biased by solubilization or reactive uptake of PFCAs to the PP filter. After assembly, each PAS is attached with Velcro to the inside of a weatherproof cap and hung outside as shown in these photos. The field blank is only exposed to the air at the site for 10 seconds, while the rest of the samplers are left up for a few weeks or months. Then they are taken down, the lids are placed back on, and the PAS are placed inside a Ziploc bag in the freezer to pause sampling. Later, the nylon filters are extracted as shown here. First, the PAS is disassembled, and once the nylon filter is removed, it is folded in half and rolled into a small triangular cone and placed inside a clean and dry falcon tube. Then extraction solvent is added, and the solution is sonicated and placed in the fridge overnight. The next day, the liquid is squeezed out of the filter, and the filter is removed and discarded. At this point, an internal standard containing mass-labeled PFCAs is added to improve accuracy and precision. And then the extract is analyzed by ICMS. Method blanks are prepared for each set of samplers undergoing analysis, and these are simply clean nylon filters which undergo the same extraction procedure without any prior exposure to the air at the field. Previous extraction efficiency experiments were conducted for TFA using extraction solvents containing various concentrations of sodium hydroxide in water. 3 millimolar NaOH in water was determined to be the optimal extraction solvent for TFA, obtaining the highest percent recovery of 83%. In these initial experiments, the extraction solvents were spiked with 400 nanograms of TFA. And this experiment was replicated for the rest of the PFCAs, this time using 2 environmentally relevant spike concentrations, one high and one low. The results for the 3 millimolar NaOH in water solvent are shown in this graph. The green bar represents quantitative recoveries of 75 to 125%. For the high concentration spike, quantitative recoveries were observed for all PFCAs, and for the low concentration spike, the uncertainty was much higher, but even so, quantitative recoveries were still observed for most PFCAs. Ion chromatography uses negative electrospray ionization, which is subject to ion suppression or enhancement caused by the presence of a matrix or other interferences in the sample. This phenomenon is referred to as matrix effects, and it can greatly affect the reproducibility, linearity, and accuracy of the method and lead to errors in quantification. The use of isotopically mass-labeled internal standards helps to mitigate these matrix effects. This is a graph of the PFPRA concentrations in passive air samplers deployed at 2 Toronto locations, and these concentrations are normalized using the mass-labeled TFA internal standard in blue, the PFPRA internal standard in green, and the PFBA internal standard in purple. And what this graph shows is that in the absence of a mass-labeled PFPRA internal standard, the mass-labeled TFA internal standard should be used to normalize PFPRA peaks, as the PFPRA recoveries using the PFBA internal standard were less than half compared to those using the PFPRA internal standard. And ultimately, the key takeaway from this is that the choice of internal standard can be extremely important to the accuracy of the analysis. Previously, our PAS have been deployed at urban and remote sites for year-long studies of temporal trends. Triplicate samplers were deployed in Toronto at York University and at 2 remote sites, Tadoussac in Quebec and Saturna Island in BC. All locations showed a clear trend in which the relative mixing ratios of gas phase PFCAs decrease with increasing chain length. As you can see from the graphs, the shortest PFCA TFA, shown in red, consistently has the highest mixing ratio. And this observed trend is consistent with known sources of PFCAs, as ultra-short chain PFCAs, especially TFA, can be formed from many more PFAS compounds than their longer-chained counterparts. Another observation was that seasonal dependence can be seen for TFA, where mixing ratios are higher in the summer and lower in the winter. This was not observed for the longer PFCAs. Also, in remote locations, gas phase PFCA levels are generally found to be lower than those in Toronto, likely due in part to the many more local point sources of short-lived PFCA precursors in urban cities. For the current research, triplicate PAS were deployed at various Toronto locations to obtain ultra-trace data at the parts per quadrillion to parts per trillion by volume levels on the atmospheric concentrations of C2 to C6 PFCAs. This data will allow us to investigate the temporal and spatial distributions of PFCAs around potential sources. Measurements were obtained from 3 locations as part of the study of winter air pollution in Toronto or SWABE campaign, which was an investigation of urban air quality led by Environment and Climate Change Canada, and at one location at Pearson International Airport, which is a suspected PFAS hotspot, as well as at 5 locations in the area surrounding the airport. This map demonstrates the SWAPE campaign sampling sites. Starting from the left is High Park, then Evergreen Brickworks, and at the top right, University of Toronto Scarborough campus. This graph compares the PFCA levels measured at the 3 SWAPED sites. PAS showed similar PFCA concentrations in the tens of parts per quadrillion range, with mixing ratios for the shortest chain PFCAs, TFA and PFPRA, approximately 6 to 9 times higher than PFBA. Now onto the Pearson Airport sampling locations. This is a map of the paths the planes take when landing at one of the runways at Pearson Airport. We deployed multiple sets of triplicate passive samplers inside airport grounds for 2 to 6 months each from November 2023 to May 2024. Triplicate PAS were also deployed at 5 sites in the surrounding area to make a transect of the plane landing paths. These are some photos from the deployment. Unfortunately, the PAS from sites 1 and 2 disappeared, likely due to human interference, so we do not have data from these sites. But luckily, we have data from sites 3, 4, and 5. These are the PFCA atmospheric mixing ratios measured at Pearson Airport. As you can see from these graphs, there is high variability in the PFCA concentrations measured from November to May. PAS deployed November to January contained relatively high PFBA concentrations, while PAS deployed March to May contained extremely high amounts of PFPRA. And also of note is that the TFA concentrations over this March to May period were actually quite high compared to the other sampling periods. And even with these much higher TFA concentrations, you can see that PFPRA still dominates the March to May measurements. Overall, there does not appear to be a trend, which is different from what we see at other locations in the city or at remote sites, where there is a trend in which the PFCA concentrations decrease with increasing chain length. Pearson Airport appears to be a point source of gas phase PFPRA and PFBA. We also deployed triplicate PAS at Pearson from November to March, and if we compare those with the 2 sets of samplers deployed within the same time frame added to each other in this graph, you can see that the PFC concentrations are comparable at the tens of parts per quadrillion levels. And this increases our confidence in passive air sampler measurements over different timescales. This graph compares the PFCA concentrations measured at each of the sites surrounding the airport, where the PAS were deployed over the entire sampling period from November to May. As you can see, there is high variability in TFA measurements from site to site, but the other PFCA measurements are similar to each other, all in the parts per quadrillion range. Site 4, which is a rooftop at York University, seems to have the highest concentrations of C2 to C4 PFCAs, and in particular, the TFA mixing ratio at York is more than twice as high as at the other 2 sites. This may indicate that York University is a point source for TFA, and or that York is nearby larger emissions of short-lived TFA-specific precursors, or even direct TFA emissions. However, it should also be noted that TFA concentrations at York are approximately 2 times lower than at Pearson Airport over this sampling period. And the atmospheric mixing ratios of PFPRA and PFBA at all three sites are much lower than those measured inside airport grounds. PFBA levels are approximately 3 times lower, while PFPRA levels are 100 times lower than at the airport. And this strengthens the evidence for the existence of a PFPRA point source at the airport. So to summarize, the mass-labeled TFA internal standard is a good alternative to the PFPRA internal standard. For the SWAPID PAS, shorter chain PFCAs were found in higher concentrations. TFA and PFPRA dominated. The Pearson Airport PAS showed no discernible trend, which is different from other locations. And we saw that Pearson Airport may be a point source for emissions of PFPRA and or PFPRA specific precursors. Nylon passive air samplers are suitable for PFCA sampling and can be deployed nearly anywhere, which will allow us to gain valuable information on the concentration and long-range transport of gas phase PFCAs in a variety of environments. We can then begin to monitor PFCA depositions over time and eventually make a heat map of PFCAs throughout Canada or even North America. And now that we can measure PFCAs in the atmosphere and are confident in the results, we can start to study PFCA deposition rates and quantify deposition fluxes. I'd like to thank everyone in the VDB and CJY research groups at York University, in particular Mayre and Daniel. Also a big thank you to the team at Environment and Climate Change Canada for all of their help. And thank you to the listed organizations for providing the funding for this research. Thank you all for listening.
Are there any questions in the room? Yeah.
Thank you. Great presentation. I have many questions, but I'll ask only one because I don't think we have a lot of time. How did you estimate the volume of air sample to calculate the concentrations? And did you compare with the PAF samplers for which there's known sampled air volumes?
No, for these we did not do any comparisons with the puff samplers. And we just left the samplers out for a set amount of time. We didn't estimate the volumes. And in order to calculate the concentrations, we use these predicted dose responses for each PFCA.
Yeah. Can you pass this? Absolutely.
Thank you. Did you see any, did you look at the aerosol phase, and did you see any of the shorter chains in the aerosol phase?
We have not looked at the aerosol phase, at least not for my my research. Just looked at the gas phase for now.
We're over. Sorry, Martin. Sorry, Marta. You'll have to ask later.
Great. Well, thank you very much, Irina. Okay, let's now welcome our next speaker, Chungyan Lee from the National Central University.
Hello everyone, my name is Zhongyan Li and I'm from National Central University, Taiwan. And my topic is about developing a statistical model to explore the influencing mechanism on atmospheric mercury concentration in Taiwan. And to begin with my introduction, as we all know, mercury can be transported globally through the atmospheric circulation. And in 2019, UN Environment said that East and South Asia is the major emission sources region, and Taiwan thought to be located in the downwind side of the East Asia continent is significantly impacted by the long-range transboundary pollutants. And recently, many studies show that atmospheric mercury concentration exhibits seasonality pattern in many places, just like in Taiwan. Mercury concentrations at both loading and NCU sites exhibit lower value in summer and higher in spring, although the specific seasonality vary by region. Meteorological conditions are considered to be key drivers indirectly responsible for seasonal changes in atmospheric mercury process. And chemical transport model such as geoscan has been employed to simulate changes in atmospheric mercury concentration and to investigate the mechanism influencing these concentrations across different regions. And besides the chemical transport models, statistical models are also useful tools in quantifying the impact of multiple factors on air quality. As a flexible model, the generalized audicting model, which is GAMS, can be introduced to environmental study for over 15 years. Like Jen and O and Zhang using this model to assess meteorological and pollutants effect on PM2.5 and GM in East China, respectively. Also, Lin at 2020 used this model to quantify the impact of meteorological factors and air pollutants on GM concentration at labs. However, in Taiwan, there are only two continuous mercury monitoring instruments. One is in lab and in Luling Mountain, and the other is at NCU. Therefore, this study, in addition to use high altitude data from the Luling station and low altitude data from the NCU station, was also integrated. And GAMS was employed to analyze and compare the effect of influencing factor on atmospheric mercury concentration variations between high and low altitude monitoring sites. And by comparing the model predictions with observation, the accuracy and robustness of the model are verified, and the potential causes of any discrepancies are explored in depth. Next is my methodology. For the sampling sites, one is located in the National Central University, and one is located in the Yushan National Park, and its altitude is 125 and 2,862 above mean sea level, respectively. And the mercury observation obtained in this study were from the Telegram system, and the meteorological parameters are from 10-meter tower. And about the pollutant parameters, one is from the loading station and one is from the Pingzhen Air Quality Monitoring Station. It's because at the NCU station, there are not instruments that monitoring this kind of air pollutant. So I use the nearest monitoring station. And for the backward trajectory, I use the NOAA high-speed model. And the data in 2019 was at both sites was used for training, and in 2020, data was used for prediction. And about the game model, the equation is do like this, and the components are listed here. And the measure is journal. In the sprite function for the smooth function, I use is which called smooth function, and the measure smoothing estimation measure is called REML, and in the sprite function, which is this in this option in this function you have the option that you can choose, and I choose a QB regression sprite for the meteorological and pollutants parameters, and the other is cyclic cubic regression sprite for the dummy variables. And the way I choose parameter is based on the AIC and R-square. AIC was used as an estimator to ensure the effectiveness of each input variables, and I use forward selection based on AIC and R-square to develop the game model. As I add parameter into the model one by one and check the AIC and R-square of the model, the AIC should be lower and the R-square become greater for the better model. And after developing the model, I use the predict function to predict the GN variation in 2020. As shown in this table, I directed all parameters into 4 subsets: dummy variable, which is month, hour, and date of year, and meteorological parameters, pollutant parameters, and air transmissions. And finally, this parameter was chosen in these 2 sites. And here comes my results. First, I want to introduce mercury distribution in Duluth Mountain. The left figures illustrate the seasonal mean in 2019 and 2020 in labs. We can observe that because of the biomass burning in spring, which caused a higher value of GN in this season. And however, in summer, most of air masses will come from the South China Sea or West Pacific Ocean, which bring the relatively clean air to labs. And the right figure shows the dino pattern in labs, and this is for 2019. We can see that during the daytime, the pollutants such as GN, PM2.5, and CO was high because it will brought to loading through the valley wind. And in nighttime, influenced by the subsidence events, the air masses come from the free atmosphere. So the higher values of GON, PBN, and ozone can be observed at labs. And for the lab model training, this figure shows the correlation between the GN fitted and by the model and the observation in 2019 in labs. And we can see that the model fitting is good, with the R-square is around 0.82. And this indicates that the model effectively simulates the variation in GM concentration. On the left-hand side, the residual plots show that the vast majority of residuals are concentrating within plus and minus 0.5, indicating that the model's prediction errors are relatively small and that the overall stability of the prediction is good. And this chart shows the contribution of each parameter in labs. We can see that the CO contributes the most, almost 72% of the GN variation at labs. And next is month and relative humidity. As we can see that as CO concentration increase, we see the corresponding rise in GN concentration. And while higher values of CO do not lead to more GN, it's important to know that the rate of GN increase actually slows down as CO concentration continues to rise. And we can see that the lower GN and GN-CO ratio may contribute to the lower increase in GN concentration. And because in spring, the biomass burning will bring more CO concentration to labs, and GN concentration it will evaluate not quite high as CO. And relative humidity can serve as the indicator of vertical air masses movement at left. We can see that the increasing trend of GN slow down when the relative humidity exceeds 7%, likely due to the influence of the boundary layer air masses. After developing the model by using data in 2019, I used 2020 data for game model to predict the mercury concentration in 2020 in labs. We can see that the R square is high, which is 0.73, and that the model predict well. However, the data distribution show that there is a threshold in the high concentration range, since the observation value exceeds a certain limit, and the predicted value stop rising. This suggests that the model has some limitation when it comes to predicting high GM concentrations, which could result in overestimating these high concentrated events. And from the residual, we can see that most of the residual fall within the plus and minus 0.5, and mainly between 0 and 0.5. This indicated that the model tends to be systematically overestimated. Sorry. And at NCU, because of the northeast wind dominate during the winter and spring, higher GM concentration can be observed. However, in summer, the prevailing wind is southwest, but influenced by some local emissions. We can see the standard deviation was higher in summer compared to other seasons. For the diurnal pattern, we can see during the daytime, because of the photochemistry reaction, GM can be oxidized into GN with high OH radical. And in the nighttime, because of the low wind speed, which make the pollutant accumulate and cause the PBN increase, PBN and GM increase. At NCU sites, for the model training, we can see from the right figure, the R square is 0.58, and it's not light head, but it's quite enough. This indicates that the model can simulate the variation in GN concentration. And the time series plots show that the model accurately capture the trend of GN concentration variation across the 4 seasons. However, it struggles to adequately track the trend during pollution events that result in the high GN values. And the residual plot indicate that aside from some underestimation, during this pollution event, most residuals fall within 0.5. This chart shows the contribution of each parameter in NCU model. We can also see that CO is the major contributor to the GN variation. And next is the hour and the wind direction. As seen in Luling model, CO concentration increase and GM concentration increase. However, while the higher the CO concentration continue to become higher, the GM concentration show that it decrease, which may contribute to the to their sources. Like from our data, we can see the CO concentration reach their peak during the rush hour, while GM concentration reaches the highest during the nighttime. And for an hour, it primarily reflects the diurnal pattern at NCU station. In daytime, photochemical reaction cause the GN oxidize to GON, and strong convection and dispersion reduce the pollutant accumulation, which lower the GN concentration. And in nighttime, lower wind speed and poor dispersion, pollutants accumulation can accumulate near the surface and resulted in increased GN concentration. At NCU, we can see that GM concentration increase when the wind direction is between south to southwest, and most of wind come from, we can see that most of wind come from northeast. And however, once there was a southwest wind, the evaluated GM could be observed. And this result is the same with Shi et al. In 2019. They used the data from 2017 August to 2019 September. And most of the known potential major mercury emission sources are located to the north of NCU. And it indicates that the unidentified but significant local emission source located in the area between south to southwest of NCU. The prediction in 2020 at NCU, the R square was 0.49, and when observed GN were high, the model often struggled to capture them correctly, and residual plots highlight the variation in prediction accuracy, with most residuals falling within plus and minus and plus 0.5 range. However, during the pollution event, we frequently see the residual dropping below minus 0.5. This indicates the notable underestimated issues in the model when it comes to high concentration GN. And this chart illustrates the contributor of each parameter to the variation in GN. We can see that at lab CO contribute the most, and RH later is RH month, hour, and wind direction. To sum up, from the observation at labs, GN concentration were higher during the daytime and in spring, however lower at nighttime and summer. And NCU, GN was higher in the cold season and lower in warm season. And I used the 2019 data to train game model. And we can see CO contribute the most at both sides, and RH at labs, and hour and wind direction at NCU. And for the prediction, at labs was overestimated, and at NCU it is underestimated. Thank you for your attention.
I am going to ask that if you have questions that you find, get together and ask during the break, which comes after this next talk, so that we can start the next talk quickly or straight away.
Thank you very much.
Is this one on?
All right, folks. Great. We have our last talk before the break, and this is another online talk. Let's welcome Hossein Foroutan from Virginia Tech.
Okay, hello everyone. My name is Hossein Foroutan, Associate Professor in the Department of Civil and Environmental Engineering at Virginia Tech. And I'm excited to talk about our recent research into quantifying the atmospheric deposition of microplastics in our area in South Central Appalachia. Before getting started, I'd like to acknowledge my co-authors, most of them from Virginia Tech, and most of them are graduate and undergraduate students, especially Adam El-Nahas, who led the research and work into developing the methodology and data analysis. So let's start with the concept of atmospheric microplastics. Atmospheric has recently emerged as the environmental compartment important for micro and nanoplastics. And people start to really realizing the fact that these small pieces of plastic can become airborne and might be inhaled by human and animal, may be transported long range and deposited into crops and waterways. So atmospheric deposition now becomes an important factor into the budgeting of the plastics in the environment. Once in the air, microplastics and nanoplastics can transport long distances and affected areas that previously known as pristine or clean, far away from any obvious human interaction. They can also transport other types of pollutants with them. Heavy metal and even PFAS are shown to be able to absorb into microplastics. And then finally, once in the air, they can interact with other atmospheric constituents, for instance, with aerosols and clouds. So considering this important aspects of micro and nanoplastics, people start to look into sampling microplastics and nanoplastics in the air. So this review came out about 2 years ago, look into all the different atmospheric sampling, classified and categorized as air concentrations, and in other words, active sampling, basically pumping air over a filter. Most relevant to this group, deposition sampling, so basically more of passive sampling. And then the surface sampling means that you go out there and basically sample the surface of a soil or some other types, just to see what deposited before. So I want you to take a look at the triangles now, and really the take-home message for me when I was looking at this 2 years ago is first, you see that the range of these concentrations, in this case, numbers per meter square per day, are orders of magnitude different between different locations. So really the heterogeneity of this deposition. And then the other point that I noticed is that essentially in the United States, we don't have any study in the Eastern United States. About a couple of years ago, the study looking into the Western United States came out, and in fact used the size at NADP to quantify the position of microplastics in the western part of the United States. But we, as you see in the map, we don't have really anything in the eastern part. So us being at Virginia Tech and the eastern part of the United States, we were curious into understanding how much microplastics really deposited in our area. And if you've been to Blacksburg, Virginia, in Southwest Virginia, you know that we're living in a very rural region. So it's a perfect position to look into areas far away from obvious human effect. So again, the blow up of the Appalachian region in the United States here shown, and the Appalachian Commission divided this region into a couple of sub-regions based on the topography and demography of these regions. So again, the Blacksburg area is in the south central Appalachia here shown in the magenta color. So we essentially want to know what is the deposition of microplastics in this region. So what we did is we basically started doing the sampling in 2 locations. Hereafter, I call them NADP site and Key site. I'm going to talk more about these 2 sites. But essentially, the goal of our research is to quantify and characterize atmospheric microplastic deposition in these 2 regions and essentially understand and quantify what's happening in the South Central Appalachia. So we picked 2 locations about 11 miles apart. The first one hereafter, I call it NADP site, is in fact the NTN site VA13. And here is a great opportunity to thank people at NADP and NTN with being really open into letting us access this site. And I want to acknowledge that that openness to these new directions. The other site that we pick is hereafter I call it Keys or Kentland Farm. It's a site in a farm operated by Virginia Tech, and we basically wanted to see if there is any clear heterogeneity in terms of the deposition between at least these 2 local locations. We conducted passive sampling using a 12-liter stainless steel beaker, and there are studies into using different types of containers, and beakers shown to be like a good sampling device, as done with other depositions done by the NADP to collect these microplastic. Obviously, we want to go with the stainless steel because of the reducing any contamination from any other types of plastic container being used. We let the beakers out for 21 days. Any sampling period was for exactly 21 days, 3 weeks, and we did 5 sampling events between March and September of 2023. So essentially, at 2 locations, you will get samples that are shown here, 5 times 2 get 10, and then for each sample we did a field blank. It's really important for the microplastics because, as you know, there's a lot of contamination from all the everything, basically from your clothes all the way to your lab environment and everything. So it's really important to reduce the field blight. So essentially we have 20 filters, and we went through a detailed processing of these samples, hydrogen peroxide digestion, then visual identification, and essentially eventually using the Raman analysis to understand or confirm the plastic and the type or polymer type. So without going through the details, instead of having these details, what we did is we developed a tutorial, a step-by-step tutorial. I put a QR code in here for you that works toward standardizing our methodology for collection analysis of atmospheric microplastics. And we think that's a very important, and I got back to this point of the lack of a standard protocol to collect and analyze microplastics. So we try to take an attempt into help with the community move towards the standard method. And again, I got back to this point at the end of my talk. So moving forward, these are some results from our deposition rate. So as you see in this table on the left, 5 sampling period, each 12 days, each at 2 locations at exact same time, NADP and key sites, and the numbers shown here, which also what you see in this bar chart is number of microplastics per meter square per day. So numbers changes between 30 something all the way to 100. And this is taken into account the number of field blank that we subtracted from what we see in here. So on average, you see that something around 50, 60, some to 70 number of microplastics per meter square per day is deposited in these regions. We look into more detailed understanding what type of polymer they are formed of. So what we see is the majority of them are 3 types of microplastics, 3 types of polymers: PET or polyethylene terephthalate, polystyrene, PS, and polyamide are the top 3. In a lesser amount, we see PE, rubber, which is expected to come from the tire particles, and then PTFE is shown here. So these are in terms of the polymer type. And then again, compared with the 2 different, or break into 2 different sites. We also looked into shape. Shape is also very important, not only from the exposure point of view, that important to the inhalation, but also from the long-range transport. Again, the majority is similar to a number of other studies, is shown to be fiber. We see 51% fiber, 40% fragment, and with a lesser amount fill, which is in accordance with the number of other studies across the globe that they've seen fibers and fragments to be the majority of the type or shape of the plastic. We also looked a little bit deeper into the aspect ratio, and interestingly, we see that it's following a very closely linear form with the lens. Again, this is somewhat expected because as the microplastics or fibers in the environment start to age or weather, they start to break down. So longer microplastics in lens also associated with higher aspect ratio, so longer fibers, and as they degrade and weather, they start to break down and their aspect ratios start to become smaller and smaller. We also take a look at the size distribution, and here I'm separating into the fiber and fragment size. For the fiber, the majority of the fibers, more than 25%, was seen between 200 and 400 micron, with the range being 150 to as long as a 3,000, 3 millimeter size, like a very long fiber. For the fragment, the majority of them sits between 50 and 100 micron, as you see on this panel on the right. And again, the range for fragment was between 40-ish to 230 micron. We bring in all this data that I showed you in the previous couple of slides all together to better understand the settling velocity of the microplastics. And what you see here in the x-axis is the equivalent diameter, and equivalent diameter is the volume equivalent diameter, letting us basically to plot fragments, fibers all together into one plot. So it takes into account not only basically it takes into account also the shape of the plastics. And on the y-axis, we have the settling velocity, which is not only a function of density, but also a function of the shape. So basically bring everything all together into one graph. And you see the fibers, these orange dots are mostly laid between 0.01 and 0.1 meter per second in terms of settling velocity, and the fragments is 1 order of magnitude more, between 0.1 and 1 meter. So essentially, you see most of the orange dots are 1 order of magnitude, orange dots are fibers, 1 order of magnitude lower than the blue triangles, 1 order of magnitude more. In other words, on an average over these 5 months, take into account everything, density and shape, we conclude that the settling velocity of fibers is 1 order of magnitude less than those of fragments. And we did some back of the envelope calculation based on the boundary layer thickness, assuming that they're distributed uniformly in the boundary layer. We roughly estimate the residence time against dry deposition of the fibers to be in the order of 5 to 55 hours, and for fragments in the half an hour to 5 hours in terms of the residence time. So we also look into the annual deposition, kind of scale this up and see what it means for the larger area and longer period of time. So we conducted a Welch two-student test between the 2 locations, and we didn't find any statistical significant difference between the 2 deposition rate between the 2 positions. So what we consider is that we basically then, in another word, at least for the 11 miles apart, and at least for those 5 periods that we looked into, we didn't find any seasonal or spatial difference. So we basically then for that time averaged the value of the deposition, and we reported the average daily MP deposition rate of 68 microplastics per meter square per day. Now, this value in terms of the annual deposition, if you want to scale this up and think about put in the context of other deposition rates, is in the order of 0.03 kilogram per hectare. And if you want to scale this up for the region of the South Central region of Appalachia, again, the magenta region in the map, you're talking about 321 tons of plastic per year deposited in that area. This is the area resided by about 5 million people. So it's really try to put that into context of what it means for people in there. And again, most of that is pretty rural areas. There's no major city being in there as the source of microplastics. So let's summarize what we covered in this talk. So we present the first study into the atmospheric deposition of microbial nanoplastics in the eastern US, specifically in the Appalachian region. We conducted 5 sampling periods, each 21 days between March and September, measuring the total deposition. And we estimated, as the first estimate, in this area of 68 microplastics per meter square per day being deposited in this area of South Central Appalachia, which means roughly in the order of 300 tons per year. Again, this is one of the samples, one of the fibers that we saw. We see a long red fibers, that the actual fiber that was detected. We take a good care into removing the background, being very mindful, very careful with our analysis, and try to really follow, although there is no uniform or standard method, we try to go as close as possible to some of the well-established studies. And in order to help the community to start to have something very detailed to start with, we developed this step-by-step tutorial that basically any student or any researchers can start on step-by-step with all the details, really follow and hopefully get results in a different setup that can be compared directly with our results. So that's something that I wanted to highlight in here. Couple of personal thoughts at this point, and I'm happy to kind of follow up with these either by email or when I'm there online to answer any questions or follow up that you guys have. I think we're getting to the point that we really need to think about measuring microplastics and nanoplastics long term and in a number of places. I think really the process or the story is similar to what's happening to PFAS that a few years ago, no one was thinking about measuring PFAS from the air deposition. But now there are attempts into looking into PFAS, and I think microplastics and nanoplastics going the same direction. I think it's perhaps time to implement a pilot study, maybe for a limited number of sites in the NADP, to look into the deposition of microplastics. And I think NADP is uniquely positioned to tackle this because of the infrastructure that's already in place, the long history to standardizing the protocols and methodologies that basically can be used to compare site to site. And again, coming from the microplastics community, I think this is one of the most important barrier into this research, that really study from one side is hard to compare to the other. So really having a protocol standardized is the most important step towards that. So again, I'm happy to start the conversation. I put my contact info down here. It's an easy email, hossein@bt.edu. Please follow up with me if you have thoughts, if you're interested into looking into that issue. Again, I'm happy to follow up also in live part of the sessions with any questions and thought that people may have. So with that, I stop here, and I'll be happy to answer any questions in the live session. Thank you.
Okay, so I've just been told the food's out there, caterer's leaving at 4. So those of you who do not have a question or do not want to hear, start using the doors. Those of you who have a question, please raise your hand. We will be back in here at 4 o'clock to restart. So are there any questions for Hossein about microplastics?
I have one question, John.
Yeah, someone?
Yeah, I'm wondering if you have seen any information or evidence that might suggest that inhaling plastic microfibers would have an impact like inhaling asbestos does. Like, is there any risk for mesothelioma or other health effects?
Yeah, that's a great question. I think the health impacts of the inhalation is emerging as we were talking. So very recently, talking about earlier this year, microplastic or nanoplastic has been found deep in the lung. So we are at this stage that at least we know that inhalation is a pathway for microfibers to get into the lung. Again, earlier this year, as I said, these are all very new studies. A new study in the New England Journal of Medicine, which is the New England Journal of Medicine, found microplastic in blood can form plaque around them and basically cause the issues with the cardiovascular system. So again, like any other pollutants, and you had a great example of asbestos, we are probably at the point that we were really starting understanding that was an issue with asbestos, and we're right there. More studies needed, more epidemiological study as well as incidence studies needed. But as an environmental engineer, I think my goal or my role is to be able to show that it's actually in the environment and it's in the air. So hopefully that helps.
Thank you. There's another question in the room. Marta?
Thanks. Great talk, interesting idea. Mine is a mix between a question and a comment in the sense that I think it would be interesting to also measure the nature of the microplastics rather than just the size and the numbers, because microplastics can act as accumulator, like a passive samplers of chemical pollutants. And I wonder if you have been thinking about it, and maybe it's a suggestion if you implement these measurements to also look at the composition and the chemicals absorbed on the microplastics.
That's again an excellent point. I think at this point our goal was to make sure that we detect the microplastics and confirm that they are actually microplastics. And during this process, we had to include the hydrogen peroxide to digest the organic matrix over that, because oftentimes you find microplastics heavily degraded, covered in biofilm oftentimes. And essentially, in a way, you mess with your sample because you want to dissolve everything and uncover so you can actually detect the type of plastics in there. But depends on the question. The question is on the plastic itself, or is on the microbes on it, or is it on the organics or on the metals on it? I think the protocol of the analysis should change. I agree with you that that's an important point, that thinking about them not only as a pollutant by itself, but as a Trojan horse for other types of pollutants. I agree.
Thanks for the talk. This is David Gay with NADP. Very enjoyable to hear that you at once came up with a method and are saying that that's one of the big problems here, is that we don't, up until now, don't have a consistent method. It's been a big, we have talked about, within NADP, we've talked about monitoring plastics, and that's been one of the big issues, not a consistent method. So I applaud you there. And I will read through your method, certainly. Simple question, based on the masses that you were measuring in the study, do you think it could be run on a weekly basis? Do you think there's enough mass there to be run 1 week rather than 21 days?
I think so. I think so. In fact, interestingly, what I did was kind of, in order to test this protocol, this is in 2023, right? So I brought a couple of undergraduate interns, not really familiar with the step, and I give them this tutorial and say, hey, just go through this tutorial and see if you can do this. And since they're kind of had a shorter time, because we wanted to finish this only for the summertime, we changed that. Everything is the same, only do this for 1 week. And we actually changed this two differences. One, that change it in 1 week, and change it, instead of having it also at the key side, like rural area, we also do it in the downtown Blacksburg, which is, again, I mean, if you've been to Blacksburg, I mean, downtown is like not like huge. But the interesting thing is that, back to David's point, we did find enough mass to show that plastic is deposited. And suddenly we found a lot of tire in downtown. So that's another really interesting point to think about, the tire particles in the urban areas and the importance of them in the umbrella of microplastics.
Right, so you were identifying with the same analysis.
Yeah. And undergraduate student interns were able to follow this and get the results. I mean, of course, we get feedback from them. That's part of the result. Like hear from them that what are the parts of the protocol that they think was not clear. So we work on that.
Mm-hmm. Sure.
Yeah.
Just quick follow-up. I was wondering if it's published.
Yes, so this is in review with ESNTR. We just submitted, just like it's 2 weeks ago, we submitted a revision. So should be from the journal anytime soon. So be on the lookout of the ESNTR should come out.
Thank you very much.
Yeah.
I'm now going to encourage everyone, to say thank you and go visit the snacks and drinks and be back at 4.
Okay, welcome back after the break. Hope you had a nice, refreshing snack. We're going to get started here so we can try and stay on time for the rest of the talks today. I'd like to introduce Rodolfo Sosa Echeverria from the Universidad Nacional Autónoma de Mexico. I hope I did that okay. Welcome, Rodolfo.
Thank you very much for your presentation. I'm very happy with only 3 talks to finish this NADP meeting. Be ready for the last 3, okay? This presentation talk about the collaboration between National Atmospheric Deposition Program and the National University of Mexico. We appreciate all the work that David Guy, David Grande, and all my colleagues that are working now in Mexico City in order to continue different collaboration projects with atmospheric deposition, ammonia, and in this case, working in mercury. All you know this kind of information. In this case, mercury is very important pollutant to know. It's very important because it's a several pollutants in water, soil, air, and different kinds of ecosystems. Has a background in Mexico regarding atmospheric pollutants. We only evaluate criteria pollutants. We need to pay attention in toxic atmospheric pollutants too. The history of the air quality monitoring at Mexico City metropolitan area begins during the 80s. The most important pollutants were sulfur dioxide, total suspended particles, and lead. During this period of time, different kinds of studies present high levels of lead, and this is one of the reasons why the government changed the lead and reduced the lead or avoid the lead in gasoline, because lead tretatil was used as an anti-knocking. Another very important strategy was the switching of fuel oil that was used at the power plants located inside Mexico City. The switching was to natural gas. We had a successful regarding SO2, regarding particles and lead, with what happened. When we reduce the lead in gasolines, we don't have any kind of compounds to substitute the lead. Then we increase the number of reactive hydrocarbons in gasoline, and this increases the ozone. Another point, when we switch the fuel oil by natural gas, increase nitrogen oxides. We put off the ingredients in order to increase ozone, and that is the problem that we have now. And another problem is particles, PM10 and PM2.5. Remember, we only are measuring as a regulation criteria pollutants. As an academical institutions and collaborating with some areas of the government, we pay attention in acid rain during the 80s. Start the first studies about it. However, starting the year 2000, we collaborate with the World Meteorological Organization, and coming the years, we are collaborating with the National Atmospheric Deposition Programs, continuing with different protocols. Now, we are working in criteria pollutants with atmospheric deposition, and why not to think in toxics? And mercury is one pollutant that is working by the National Atmospheric Deposition Program. And part of this collaboration starts in June of the last year, analyzing GEM using the CRAN analyzer. We received this instrument from NADP, and was located in the quality monitoring station at the University of Mexico. The middle of government of Mexico City. Equipment are equivalents or reference of EPA methodology. This is the part of the criteria pollutants. Up another part of the racks. Carbon dioxide, carbon, and we are in share of the mercury. Here appears the TECRAN that we receive for NAT. Appears another evaluation for pollutants using manual methods. At the side of the building appears a meteorological station. And this is why it's very important to maintain operating this site, because it's a super site, because we are evaluating different kinds of pollutants at the same time. How we are working in order to evaluate the data that are generated by the CRAN. We are working according with the EPA protocols. We are in touch with David Guy and David Grande. And at this moment, we are in the steps of validation 1 and 2. I am going to present here some preliminary, and we start in June of 2023. And at the moment, we are continue working with the evaluation of mercury. During the month of April, we decided to continue with the monitoring of mercury. Here you can see we have average concentrations. We start analyzing, considering all the days and all the database. And this is the information that was lost during the period of 1 month or 2 months. It's a great challenge to develop a project regarding to mercury, because we received the analyzer from United States is working directly with NADP in order to maintain the operation of this pollutant of mercury. What happened if we analyze all the information about the GEM early concentrations? It's a very interesting behavior of the pollutant. There is a peak in the morning. There is a lower concentration at 3 p.m. Another increase during the afternoon and night, but the peak is in the morning. At this moment, some people is analyzing this information, considering meteorological conditions and another pollutants. Remember that at the same site, we are evaluating another pollutants. Carbon monoxide could be a very nice indicator, or mobile sources, but we have different kinds of emission sources in this area. This is all the information that we are collecting. There's a lot of information from June to April that we present here. As specific attention, we are pointed in this big pics. Fortunately, sometimes equipment that is closer to our monitoring station operates, boilers or another kind of sources, but we need to review and separate the data that could contaminate our results. Here appears again the behavior of the concentration of mercury during the day. Is similar for all the months. There is a reduction in the afternoon. And this is the table for border results. We can observe some part of the information. For time purposes, we only are going to present part of the information. You can see that the median is the 50% of the information are very similar, but the towards they present the values, the higher values at this moment. And we will analyze the day of the week from Monday to Sunday. The levels of concentration are very similar, but from Friday appears a peak here during the afternoon. Most of the pollutants in Mexico City present a higher peak during the evening. This is called the party effects, because most of the people is going from the job to celebrate or to a meetings. I think that is similar how my friends, NADP friends, to celebrate on Friday or maybe today, okay? Why is important to have a monitoring site for mercury at Mexico City? This is a very nice coincidence because we are in touch with our friends of Taiwan. Here is Taiwan, Mauna Loa. I am very sad this site was closed. Maybe it would be possible to maintain passive samplers. But Mexico City, we are in the same latitude. Here. All the other sites in United States are at the north of this site. And of course, in Alaska, it's at the north. We are doing a lot of efforts in order to maintain these monitoring sites working. And in the future, we're planning to present this information. This is a resume of information that David Guy sent us in a presentation in Mexico City online regarding to the 2022 results of the atmospheric mercury network, the results of gaseous oxidized mercury. In the future, we would like to evaluate particulate mercury. At this moment, another friend from NADP, David Grande, he's working in the validation of the information that received. And I hope that in a few months we can to present the valid result of this collaboration with the NADP. These are preliminary conclusions. The maximum mercury concentration is in the order of 20 nanograms per cubic meter. We present here the levels of during the days. And if we compare this information with another sample sites in the United States or another place in the world, they are similar with the information with urban sites. Some of the monitoring sites for mercury are located in remote sites, but this is a representative of urban sites. It is worth mentioning that the monitoring site at the University of Mexico, here appears the campus. This is the library of our university. This corresponds to school activity, but is inside a urban area. It's also recommended to increase the number of sites for measuring mercury in ambient air and in industrial areas and in regions of international interest, such as the Gulf of Mexico. And of course, it's necessary to consider methodologies such as passive atmospheric sensor to increase sampling coverage at the lowest possible cost. This is a common problem, the cost of to evaluate air quality of atmospheric deposition. What happened with our group at the UNAM? We are thinking continue with international collaboration. Remember the program here at NADP, CTDEP in North America, reactive nitrogen evaluation, include ammonia measurements in ambient air. And this is the area of the Gulf of Mexico. This is the Veracruz state. We are in agreement with the government of the Veracruz state in order that at the air quality monitoring station located in these states, we locate at the same place with atmospheric deposition sampling, and why not mercury sampling and ammonia sampling. But which kind of methodology would be possible to use with passive samplers? The cost of the automatic analyzer is higher. This is the proposing of a Trans-Pacific Passive Mercury Network. We hope that in the future we can participate with NADP and with different networks in the world. And the objective of passive sampler is a great challenge. Sometimes we think that passive sampler is a low-cost sampler, okay? The sampler is low cost, but we need to think in the laboratory. The laboratory is very important and has a cost, of course. Okay, now I finished my good intention regarding to mercury. But this is, I would like to present here the collaboration, we start the sampling with passive sampler, with alpha sampler that received from Dr. John Walker, and start the sampling in November 5th, 2 days ago. This is the campus at the UNAM. Is located at the roof of the air quality monitoring station. I hope that maybe in 1, 2, 3, 4 months, I don't know exactly, we can to start the measurement of mercury by passive samplers. Not only Mexico City is one of the most populated cities in the world. We have anthropogenic sources of mercury, and we have natural sources. In this picture, you can observe the volcanoes during the winter. 2 volcanoes. One is the Iztaccíhuatl to the left. Iztaccíhuatl is in Nahuatl or Azteca language, not in Spanish. And the meaning is a sleeping woman. And the other is the Popocatépetl, is the smoking mountain. But Popocatépetl is an active volcano. And the other, the sleeping woman, is not active volcano. At Mexico City, we want that the sleeping woman continues sleeping because it will be dangerous to be active, okay? And thank you very much for your time. You have any question, I will be happy to answer.
Yeah, I think it would be important to get you involved in the passive measurements if we can. And once we get the data corrected, me, you, and Vid will start comparing it maybe to Gurong's site. That'd be an interesting comparison. Both very urban, same latitude.
Thank you. Any other questions in the room? Then I'll ask Michael to.
That's a comment. Thank you, David, for your comment. And at the same place, we evaluate criteria pollutants, with atmospheric deposition, ammonia, mercury. We can to increase the number of pollutants. And we are taking in another places in the region of the Gulf of Mexico. The region of the Gulf of Mexico is very important as an international level. United States, Mexico, and Cuba.
Thank you.
Thank you very much.
All right, well, we're on to our last talk of the afternoon. I think everyone knows my co-chair, John Offenberg from EPA. He will treat us to a bit of a talk about PFAS here.
And in the spirit of saving the last to go last, I'm now going to return us to PFAS. A much different timescale I'm going to talk about, and want to change your or help you explore changing your thought processes and distance scales in terms of atmospheric deposition. I'm going to talk about using a very fast instrument to look at some compounds of the huge suite that we refer to as PFAS, perfluoroalkyl substances. I'm going to jump through a couple of these to get to the why we're using chemical ionization mass spectrometry. There are a couple things. It's really fast. It's highly selective for PFAS compounds, selective for those compounds that have an OH. The ionization is very soft, and we're using iodide, which is mononucleotic, and we've got all these fluorines, which are mononucleotic, or naturally mononucleotic in both cases. And so we end up with soft ionization, very clean mass spectra, very amenable to time-of-flight mass spectrometry. We're doing online gas phase analysis, recognizing that that's an operationally defined, that which makes it down the tube and into the ionization chamber and hits the detector is what we're calling gas phase. And when I say fast, I mean blazing fast. The instrument's running at about 20,000 hertz, And we're averaging, people typically average to 1 hertz. In this case, we averaged to 1/3 of a hertz, and then recorded that and offline processed 5-minute chunks as single values. And there's some play in that idea, or those ideas, with the limits of detection that we're struggling with, that we haven't solved yet. We need to, and I'll get back to this later, really need to work on how to calibrate this instrument. That's the top 2/3 of a chemical ionization mass spectrometer, essentially made by 2 companies using the same hardware, Aerodyne and, the name's escaping me, out of Switzerland. Toffwork, thank you. Make the front end and back end and sell it essentially the same instrument, marketed the 2 different ways. I've personally been working on this idea for about 5 years or 6 years, so this is the first time I get to speak about it because we've gotten to the, hey, this may actually work in the ambient air. And that's an oddity of where I'm working in PFAS, but this is our first deployment, which has bumps and warts and wiggles and hairs and all of that, but that's okay. And essentially, and I now recognize that a graph or a little animation does not work so well in PDF form. You're not going to see it. We're ionizing with, we're taking methyl iodide, cracking it apart to I-, and that I- either adducts or strips a hydrogen off of the OH containing compound of interest. We only look in terms of PFAS at the iodide adduct to simplify the post-processing work. It typically comes out to 90-some% as I- adduct. So we're calibrating with that. We're observing in the ambient atmosphere with that. And at least for this first pass, it's much easier and faster and works well. As the first deployment and in the Office of Research and Development, and noting that there are ongoing enforcement actions, I had to thread a needle here by going to federal land in a location where I might hope to observe these compounds. And near the top of my list was an EPA ORD facility, which is on the property of EPA Region 2's laboratory facility in Edison, New Jersey. There are likely, and we're not going to get into this, likely a couple dozen sources of PFAS, generally in the area within 100, 150 kilometers, from chemical manufacturing facilities to a very large newspaper printing facility to firefighting training facilities, a large fabric coater, et cetera, et cetera. But I had to stick to our own property, so to speak. For those of you who forget where New Jersey is, it's a very urban. For those of you who have not been to the Edison facility, it is a very large, it's currently 4,000 acres in central New Jersey that is former U.S. Department of Defense, U.S. Army. It's where they loaded tanks to leave North America to go to the Second World War. It does have groundwater and soil contamination issues, likely dating to that era, along with some metals and some other things. But it's highly urbanized, and to my knowledge, none of those potential sources that I mentioned are on this photograph. It's a suburban warehouse, close area. This is what we did. We put a SIMS in the back of in the white trailer, pulled it up to New Jersey, parked it in the biggest field we could find. We were given one 120 volt AC outlet, which is insufficient to run 15 amps of stuff going on the instrument. So we brought along a solar trailer, essentially to run the air conditioner for that white trailer. Again, bumps, wiggles, warts. Is there a way that I can? Nope. See it's just an instrument sitting in a trailer with a fan blowing on it. And panel C really is 15 amps right at the limit of 15 amps of working. But it did work, and the air conditioning worked well enough to keep the temperature pretty much stable. In panel B, you can see there's a don't fall off the top of the trailer railing. And on that, there's a black tube that comes up through the hole in the ceiling, or the hole in the roof, turns and is belted onto the railing, goes out a few inches, and there's a T. The funnel, downward-facing polypropylene funnel, is the inlet, goes up to a T that can flow air into the inlet, coming from a clean air tank, and that was done once every 2 hours for 10 minutes, and that was probably insufficient. The 5 liters a minute that goes down into the trailer goes through a heated transfer line that is polypropylene. For those of you that work with PFAS, that makes a lot of sense. For those of you who don't, keep scratching your head, you'll get there. 40 degrees C, which is not perfect, and we're learning along the way. Part of that has to do with calibrations. The state of the art, and it's tough not to laugh and say that at the same time, is manual syringe injections into the inlet, where you've installed a filter and you inject a single compound in ethyl acetate, put it on the filter, wait for the ethyl acetate to volatilize, and then wait for all of the single compound of interest to go down the tube and into the instrument, which is not a perfect system. And it takes a full day in the field to do that. And we had great uncertainty about how much of the compound would get stuck to the tubing and the ionization inlet and the IMR and everything. So that was done once at the end of this study. That said, the limits of detection are roughly 1 part per trillion by volume, which is great for some of you and horrible for others of you in the room. Those of you that do PFAS, maybe that's 100 nanograms per cubic meter, depending on your compound, maybe 50 nanograms per cubic meter, which is screaming high for those of us that do PFAS, and parts per trillion for others of you is ridiculously small. We only took these compounds along not knowing what we were going to see, and that's again part of the issue or the problem with the manual liquid injection. So what I'm showing here in 3 panels is what we observed, and it's largely driven by what we could take along calibration-wise and fighting the limits of detection. The top panel in pink is all of the trifluoroacetic acid calibrated data, and those blue points are the points that were above our limits of detection. Could we have messed a little bit with how we chose that definition? Absolutely. That's not the point. We saw TFA, we could see it in a few % of the time that it was the instrument was running. We saw a compound that we should have expected. The bottom panel in orange is hexafluoropropylene oxide dimer acid, HFPODA. And that single spike up to 1 part per trillion is roughly 100 nanograms per cubic meter as a lower limit. We did not remember to take along that vial of standard. So we had to come back to the lab afterward and do a lower limit calibration with N2O5 as the collisional limit as a way to estimate. So we saw it once. What the concentration is very difficult to say. In the middle is something we observed that we didn't expect to see. It's not one of the things we calibrate. We're learning how to do this. It's consistent with a hexafluoroisopropanol. And if we take these 3 and plot them in slightly different ways, it's actually the first 2. If we take all of the trifluoroacetic acid observations, including all of those, the 98% that were below the limits of detection, we can look at them on a diurnal cycle. We can do that for the gray panel in the middle, for the for the peak that is consistent with hexafluoroisopropanol, and compare it with the temperature in orange and the blue is a sum of 2 isoprene oxidation products and see that there are different daily cycles of these. We can dive into a little bit the one peak that was consistent with the HFPODA and look at wind direction and wind speed, sort of where is it coming from, but we can't say exactly where. But 100 nanograms per cubic meter is probably a couple orders of magnitude above what Martin typically sees in ambient. Your picograms? Your what? Max 10? Okay. But it begins to show that this may not be, especially in an area that we expect to be closer to some sources, may not be a constant signal. And we learned a few lessons. Trying to do this is not, if one is laying it all out on the table, I don't fully expect this to be an ambient technique in the near future until we work through the calibration and limits of detection issues. But for a fence line location or for trying to track down some stronger sources to air, this is something that we are beginning to consider in the Office of Research and Development. And I'm close to keeping us, it's a picture of, maybe I did a couple pictures so you can see them again closer. I need to point out this was work done by a postdoc with me, Jimmy Madela, who's now in the Office of Air Quality Planning and Standards in the Sector Policies and Programs Division, working on hazardous waste emissions. And yes, there's a bit of overlap conceptually, et cetera. This was published earlier this summer in the Journal of Air and Waste Management. And I need to point out that York University, University of North Carolina, and Carnegie Mellon are all working on similar sorts of online measurement techniques. Some aimed at ambient air, as York is working on, UNC in indoor air, and Ryan Sullivan's group at Carnegie Mellon is trying to add particulate measurements to the same technique, or a very similar technique in the cases. And once again, from where I work, I need to add a disclaimer. Are there any questions?
I want to correct what I just said. I was referring to precip. If you were talking in air, we're about 100 picograms per cubic meter.
Yeah, so
Threefold.
three orders of magnitude different, which is not entirely surprising. Is there a,
Online.
yeah?
Do you need a microphone?
Justin, do you have something, question?
Yeah. Hey, John, can you hear me?
Yes.
Hey, so thanks. Great talk. Putting my old EPA hat on here, you said that, this might be applicable in fence line environments, at least in the near term. Is that something you're engaging with the regional offices about that just got the SIMs and the mobile vehicles?
Not yet. There's a big jump in that, which is going from no chromatography, something that's consistent with, to an enforcement measurement or something that a state or a regional office may be able to use more strongly. This is a demonstration of, hey, we can do this. I know a very similar instrument is on the Taga trucks for emergency response. I don't know their state of development for that and how extensively they use this sort of approach. But you should talk with your regional office if you're interested and ask some questions if you think you have a use for this sort of approach of me or your regional office.
Sounds good. Thank you.
Any other questions for John? Well, that looks like it's it. Thank you.
Yeah.